respect to orientation within the nervous system. So this is the human CNS, consists of the brain and the spinal cord. And the entire CNS is symmetrical. There's a left side and a right side, and the two are basically mirror images of each other. If you look at the spinal cord, the longitudinal axis of the spinal cord is the rostral end, which is towards the front particle, and the caudal end, which is towards the tail region. There's also the dorsal surface and the ventral surface corresponding to the back, and the ventral surface corresponding to the abdominal side. With respect to the cortex, the brain itself, it has a midline, which separates the two hemispheres, left and right. Any structure located towards the midline is referred to as medial. Any structure situated further away from the midline is referred to as lateral to the midline. For our purposes today, there are certain sections of the brain that you need to keep in mind. The coronal section is seen like this, in this plane, perpendicular to the longitudinal axis of the brain. The sagittal section occurs right down the midline. A parasagittal section occurs lateral to the midline in this point. Okay. The other terms are simply alternatives, and we don't really need to know. For example, ventral can also be referred to as inferior, and so on. Now, if you look at the CNS, there are 6 major divisions. Most textbooks use 6 major subdivisions, and they're listed here, starting from the most rostral end and proceeding towards the most caudal end of the spinal cord. This cartoon shows explicitly these 6 anatomical subdivisions, the cortex being the largest part of the human brain, and other structures within the cortex, subcortical structures such as the midbrain and the eye encephalon. Further, in a more caudal direction, we have the pons, the medulla, and tucked in the posterior part of the brain is the cerebellum, which is separate from the cortex. You then have the spinal cord, which attaches indirectly to the brain via the brain stem. So let's have a look superficially and briefly at each one of these subdivisions and touch upon some of their major functions. So if you look at the cerebral cortex, there are 4 major lobes. There's the frontal lobe, which occupies the largest proportion of the cerebral cortex. It's right at the front of the brain, and that's the front, that's the back. You can always tell the back of the brain by the cerebellum. And the frontal lobe is separated from the parietal lobe, which is more posterior, by a prominent sulcus called the central sulcus. And the general term is such that sulcus, or sulci for plural, are these prominent notches or grooves. Whereas the elevations, the crests or bumps, are referred to as gyri, or gyrus for singular gyrus. Now the purple band of cortex, this narrow strip, is called the precentral gyrus, and it contains the primary motor cortex. The light green band, which is posterior to the central sulcus, is naturally called the postcentral gyrus, and it contains the primary somatosensory cortex. More posterior to the parietal lobe is the occipital lobe, way at the back. And as you then move clockwise, the final lobe is the temporal lobe, this chunk here, which lies just ventral to the lateral sulcus. So those are the 4 major lobes of the cerebral cortex.
Sorry,
Your
all right, we'll burn that before I get to the next one.
Yeah.
Okay, thanks.
It's close enough there. Okay, so
That was it,
Now, the frontal lobes are critical for short-term memory, type of memory we call also working memory. And it's also important for organizing behavior, tying the sequences of complex behavior. And I'll touch upon that later on. Parietal lobe, just behind the frontal lobe, is involved in sensing our environment, in particular surrounding sensation, touch, pressure, temperature, pain. But it also is important for a higher level of cognition that involves integration of visual information with motor tasks. For example, reaching for a cup of coffee, or recognizing spatial locations of objects in order to coordinate movements that are linked to those spatial locations. The occipital lobe, shown here in red, is critical for vision, for processing visual signals that initially come through our two eyes and then end up in the occipital lobe, get processed, and then the information then passed forward more anteriorly. But the first cortical processing station for visual signals is in the primary visual cortex back here in the occipital lobe. The temporal lobe contains two structures, the hippocampus and the amygdala, both of which are involved in information storage and information retrieval. And I'll talk more about those two structures later on in the lesson. Now, a subdivision of frontal cortex is called prefrontal cortex. And here you see the prefrontal cortex highlighted in the brains of various species, ranging from cats, dogs, rhesus monkeys, all the way up to humans. These are roughly drawn to scale. You can see the prefrontal cortex reaches its highest level of development in humans, occupies roughly a third of the neocortex in humans. And as I said before, it's important for the organization of behavior across time. We know this because lesions, experimental lesions in lab animals of the prefrontal cortex result in difficulties in initiating and executing directed behavior, purposeful behavior. We're not talking reflexes here. We're talking purposeful behaviors that require voluntary control. Not surprisingly, these lesions leave unaffected ordinary motor routines, like general IQ and memory functions outside of short-term working memory. Now, working memory is the type of memory that we use virtually every day. For example, if a friend calls you on your cell phone and gives you an important phone number to call them back at, and you happen not to have a pencil and paper, so you ask the friend to repeat that number so I can hold it in memory just long enough so that you can write it down later on, a few seconds later. That's working memory. It seems that restaurant waiters and waitresses have extraordinary working memory because they can remember just for enough time exactly who ordered what. And then once they relay that information to the chef, that information is mostly out. So that's an example of working memory. It's a temporary form of memory that is often used for planning of future actions. Now, on top of all this, there's a famous case study from the 19th century that shows dramatically a case where the frontal lobes are engaged in restraint, behavioral restraint, what I call behavioral restraint, more general category, behavioral control. And this is the case of Phineas Gage, who was a railway worker. And one day he was holding a piece of iron, an iron rod, and tapping explosives with that. Because back in those days, they were using explosives to clear large masses of land and so that they could lay down the railway tracks. And one day the dynamite exploded, drove the tapping iron right through his head. You see the exact trajectory right here. And amazingly, he was fully conscious throughout the whole incident. surviving instant. And remember, the cortex itself has no pain receptors, so apart from the pain of the flesh wound, Gage would not have suffered too much pain from the actual brain injury itself. What's interesting is that his personality gradually changed. Before the accident, he was more or less likable, sociable, easy to talk to, easy to get along with. After the accident, however, he became the exact opposite. Antisocial, very hard to reason with, more or less a pretty mean fellow to hang out with. So the conclusion from this particular case study was that the frontal lobes, in addition to all the functions I had mentioned earlier, was important for behavioral control, behavioral restraint. Without the constant activity of the frontal lobes in humans, one loses this behavioral restraint. The case also underlies an important principle, and it's that brain functions, specific functions, can be localized to particular parts of the brain. This is one of the first, if not the first case, to provide direct evidence for this notion. All right, so enough about frontal lobes. I want to move all the way back posteriorly to look at visual processing in the occipital and temporal and parietal lobes. This is actually a diagram for monkey brain, but for all intents and purposes, similar principles apply to human brain. Here's primary visual cortex. The visual information gets passed forward in two streams. A dorsal stream that terminates somewhere in the parietal cortex, and a ventral stream that terminates in the inferior temporal lobe. And each one of these streams is specialized for processing separate types of information and for mediating separate types of behavior. In the dorsal stream, we have what is essentially vision for action. And the common impairment that results from physical trauma to this part of the brain, particularly to the posterior cortex, is optic ataxia. With optic ataxia, the patient cannot convert what he or she sees, visual information, into motor commands for tasks such as reaching for an object that the patient is looking at. And an excellent case study of this is patient RV, Ruth Vickers. Female patient, she suffered a stroke. And the stroke took out large parts of her posterior parietal cortex on both sides of the brain. And to analyze the exact deficit that resulted from this injury, two separate tasks were assessed. In the first task, she had to actually use her hand to physically grab an object on the table. So in other words, she had to calibrate the size of her hand to exactly match the object so that she could effectively hold the object and take it, raise it off the table. In the other task, basically the same task, except that she was asked simply to give a manual estimation, show the investigator approximately what the size of this object is using her fingers without actually reaching up and touching the object. Okay, so the first task is an actual touch task. The second task involves no touch and just simply manual estimation. So with optic ataxia, RV, she did really poorly in the actual touch grasp calibration. Notice the flatter line here for two different sizes of objects. She did quite well in the manual estimation. Notice this deeper slope of the average line here. So she could provide a manual estimation using visual information, but when she had to reach out and touch the object, she couldn't do it. Optic ataxia. So there's a clear disconnect between her ability to use visual information and her ability to reach out and touch objects using that object location information. Now this is not a pure motor disorder, because if you ask her to close her eyes and touch various parts of her own body, nose, ear, she could do it perfectly fine. So that's what happens when the dorsal stream is impaired. What about the ventral stream? This particular stream is specialized for vision for perception. Basically, the stream processes information that enables you to assess what an object is. Whether this is a laser pointer or a pen or pencil, most of you can tell just by looking at it. That's an example of visual recognition. And when the ventral stream is physically damaged, usually you get what's known as visual form agnosia. The most common form is the person is unable to name that particular object. The verbal skills, intellectual skills are perfectly normal. It's not a vocabulary problem. They just can't name a three-dimensional object based on the visual information. Their visual acuity is perfectly normal. But there are other more subtle changes that are quite interesting. And the case study here is patient VF, who suffers hypoxia from carbon monoxide poisoning. This is an MRI scan of her brain in the horizontal section this way. These are her eyeballs, that's the occipital lobe, and you can see the white blotches here represent the regions of the brain, ventrolateral occipital region, within the ventral stream that have been damaged by the hypoxia, low oxygen. And her most dramatic symptom was visual form agnosia, and other testing was done to rule out sensory deficits and general motor control. So we asked this patient to perform what's known as a swap pattern. Basically, she was asked to hold a cartridge and then to either estimate the position, the orientation of this red swab with the cartridge using her hand and using what she saw, the position of the swab. That's called a matching task, where she simply used her hand position to signal, communicate to the experimenter the orientation of the swab. So this is her performance compared to a brain-in task control. She does pretty poorly. When she was asked to do the same task, except actually reach out and slide the cartridge through the slot, she did pretty well compared to control. Interesting, she could still match the position of the slot if she was asked not to look at the actual slot, but to imagine the slot in her brain, in her so-called mind's eye. So the conclusion here is that apparently she has no conscious visual experience. Her vision is normal, but she just cannot have conscious visual experience. She's not consciously aware of what she's seeing. And again, here's the chart. She performs pretty well when it comes to the calibration without reaching forward and actually physically sliding the cartridge into the slot. She does quite poorly when it comes to manual tasks, the motor tasks. Sorry, she does quite well with the motor tasks, but poorly with the manual estimates. And just to push things further with with visual agnosia, you present her with an object, a real object, ask her to look at it and name it. She can't do it. She tries to squirm out of it, work around it by describing it. And this is an exact quote of the description. It's not a vocabulary problem. If you then ask her to copy a diagram, in this case an apple and a book, she can't do it. She does poorly at it when she looks and copies. If, however, you ask her to draw an apple from memory without actually looking at an apple or a picture of an apple, she does it very well. So it's a disconnect between conscious visual experience and communicating that experience to the viewer. So to summarize, when the sight of damage is in the ventral stream, motor action is perfectly fine, but perception is impaired, resulting in visual form agnosia. Remember, the ventral stream is specialized for analyzing what an object is. The dorsal stream, in contrast, is specialized for visual motor function, analyzing where an object is located in order to link that information with impending motor actions. And there you've got the opposite changes. Perception is okay, but action is impaired. And that's called optically tested. Are there any questions so far? Another impairment when it comes to unilateral damage to the parietal lobe is called hemi-neglect. So in this case, the right parietal lobe was damaged in a patient. And what happens is that when they were asked to paint their environment, certain objects, they totally ignored the left half of their visual field. And the right half of the brain controls the left half of the visual field. The right half of the brain controls the left half of your environment, visual field, and vice versa. So this is a case of hemi-neglect, and there are famous case studies that you can read about in some of the books of a clinical neurologist named Oliver Sacks. He's famous for his work with neurological patients, and in some of his books he describes some pretty dramatic examples of hemi-neglect as well as of visual agnosia. He has a famous book called titled "The Man Who Mistook His Wife for a Hat." So, an extreme case of visual agnosia in which a man repeatedly identifies his wife with literally a hat. Okay, so we talked about parietal and frontal lobe. Now I want to move on to the temporal lobe. And as I said earlier, there are two major structures to make a note of. And they're both tucked underneath the temporal lobe. You can't see them because they're not on the surface. You need to look ventrally, tucked inside the temporal lobe. The larger of the two is the hippocampus, shown here in purple. The human hippocampus is about the size of your thumb. And at the rostral pole of the hippocampus lies the amygdala, shown here in red. The hippocampus, as some of you might know, is critical for the ability to learn and remember new facts and events. The amygdala plays a key role in recognizing and expressing fear. What happens when the hippocampus is damaged? Invariably, you get amnesia, which is memory loss. And I'll talk more about amnesia in my third lecture, February 2nd. So there are two major classes of amnesia. retrograde and antegrade. With retrograde amnesia, information that's acquired before the time of injury is lost, shown here in this graph. Here's the time of injury. Most of the information immediately before the injury is lost. And there's a temporal gradient for retention. So your childhood memories made long before the injury are more or less retained. Which proves one thing, one important factor. Hippocampus is not the final resting place for our long-term memories. Eventually they get moved out into the cortex. You also have antegrade amnesia, in which you can't make any new memories whatsoever. Now these are two ideal cases. In the real world, most amnesic patients show a combination of both. And there's a process known as memory consolidation. Much of what we learn gets put into short-term memory, and only the really important stuff that we need to retain gets put into long-term memory. That process of converting short-term memory into long-term memory is called consolidation. And the hippocampus is critical for consolidation. And generally, consolidation takes a certain amount of time because certain processes need to occur that take time. Biochemical processes, synaptic changes, whatever. And very often, mental rehearsal is all that needs to be done in order to convert short-term into long-term memory. Short-term memories into long-term mental rehearsal. This cartoon shows dramatically why the hippocampus is called the hippocampus. Here's the human hippocampus. That's the seahorse. And the French word for seahorse is hippocampus. The most famous case study that really opened up the entire field of memory research, brain systems and memory research, is the case of H.M., now known by his full name, Henry Gustav Molaison, who passed away about 4 years ago. And this is a photo of H.M. at about the time when he had his temporal lobe surgery to relieve symptoms of epilepsy. And this is a more recent photo in 1980 in the nursing home. And H.M. is extraordinary because he displays severe antegrade amnesia, couldn't make new memories even for a few minutes. Brenda Milner, the Canadian psychologist who examined this, who really pioneered the memory research field back in the 50s, she keeps telling the story that every time she would leave the examination room during a verbal exam of HM, she'd re-enter the room and have to reintroduce herself a few minutes later, as if they had never met, because HM could not remember her. Now, back in the 50s, they had no idea what the role of the hippocampus was as far as memory was concerned, so they too liberally, removed large sections of temporal lobe, including the hippocampus. So they inadvertently created this antegrade amnesic syndrome in HM, and you can see the drawings of HM's brain now in a more recent MRI scan of HM's brain and of the normal brain. You can see the normal brain is coronal section to get the intact hippocampi here, and a large black hole in HM's brain. Now, HM's procedural memories are perfectly intact. You can learn motor tasks, such as learn how to draw an image, copy an image of an object. So his motor skills were perfectly intact. It's just that he could not make new long-term memories of facts and events. So what this led Brenda Milner to conclude is that the brain structures that underlie explicit and implicit memory, two terms for facts and events versus procedural tasks, are not the same. They must be mediated by different structures. And it's important to note that more than just the hippocampus was removed, the surrounding temporal cortex was can't exclusively ascribe this particular form of amnesia to simply loss of just the hippocampus. That's an important conclusion that Brenda Miller correctly pointed out in her paper. Nonetheless, because of subsequent research, we now know that the hippocampus does a lot in addition to making real explicit memory. For example, just as a footnote, more recent research has shown that hippocampal patients can't imagine the future. If you were to provide them with a set of facts and ask them to imagine a future scenario, they can't do it. And I found that simply mind-blowing. Clearly the hippocampus is needed for making new memories. But I would never imagine that hippocampal patients couldn't imagine the future. So again, procedural tasks are perfectly normal. This is a graph plotting the learning curve for HM. Right hand, left hand. HM is clearly right hand. Number of errors decreased with practice over 3 days. And simply, he was asked to look in a mirror, look at a mirror image of this object, the star, and use only the mirror image to copy the star. And that's not easy trying. You get a similar learning. So his procedural memory was intact. He's able to do these more. Just couldn't make it. That's a clear, specific result. So there are multiple memory systems. And different brain structures mediate different types of information processing that lead up to information storage. So you have structures like the cerebellum and the striatum mediating the learning of motor skills. For example, playing a musical instrument involving skilled use of the fingers requires a striatum and cerebellum. The amygdala also falls under implicit memory because they mediate emotional responses and the ability to recognize those emotions and also to express them. So what happens if you suffer damage to your amygdala? Cases are relatively rare, and this is one exceptional case of a patient who has a condition known as Urbach-Wiethe disease, in which her amygdala on both sides of her brain, bilateral lesion, became calcified. And the overriding symptom there is she was unable to process facial expressions of fear, specifically fear. These are MRI scans of SM's brain at the level of the hippocampus, see intact hippocampus, and at the level of the amygdala. And you can see these white arrows of the amygdala are significantly damaged. So if you compare the performance of SM shown here in this graph, in the right-hand graph, with the performance of brain impact controls or of patients with unilateral amygdala damage, right or left amygdala, you can see that they all perform at more or less normal levels, except for SM. She had a very poor performance in rating expressions of fear. So she couldn't correctly recognize expressions of fear. Other emotions such as happiness, surprise, anger, disgust, and sadness were readily recognized at the same level as control and at the same level as unilateral patients. So loss of your, or rather trauma to both your amygdala will severely impair the ability to recognize fear. Fearful facial expression. You could do a similar task and ask the patient to actually sketch out on a piece of paper various emotional expressions, facial expressions. And these are actual pencil sketches performed by SM of various emotions. And you can see in box structure, she fails miserably when she's asked to sketch facial expression of fear. Now, for some, maybe infants are terrifying, especially if you're faced with the prospect of raising them to reach the teens. So now let's take a look at some of the structures well inside the cerebral cortex, the neocortex. So if you take a coronal section of the human brain at this level, see this vertical line here. This is the back, that's the front. And then you flip the two halves apart and you look on the coronal surface. This is what you see. And these structures, the cardiac nucleus, cutaneous, globus pallidus, and these three structures are critical for producing movements, controlling movement. And in Parkinson's disease, which I think you may have a lecture on later on, the circuitry that coordinates signaling between these structures, that circuitry is messed up. The internal capsule is a thick bundle of white matter, axons, that sends fibers from the thalamus to the cortex. So the thalamus is the major relay station, sensory relay station. It receives all sensory signals with the exception of olfaction, and it processes to a certain extent and then passes them on to the correct cortical region for further higher level processing. Notice the naming of fibers, in case you run into more neuroanatomy later on. Pathways are named in a logical fashion. So thalamocortical means exactly that. The fibers originate in the thalamus and terminate in the cortex. You can also have cortico-thalamic fibers, which originate in the cortex and terminate in the thalamus. So there is a logic to all the chaos. You can see that. So we leave the cortex, and now we get the spinal cord. And basically, the function of the spinal cord is to collect a massive amount of sensory information from the periphery, send the information up towards the brainstem, cerebellum, and cortex for processing, and also to collect motor commands from the cortex and send them back to the muscles to produce movement. That's the function of the spinal cord. You take a cross-section of the spinal cord and look at the cross-section, you can see a typical, classic butterfly pattern for the gray matter, the dark butterfly pattern, consists of cell bodies of neurons. The white matter that surrounds the butterfly is white because it consists of myelinated axons, which appear white under a microscope. So these axons run up and down the cord to relay sensory or motor commands respectively to and from the nerve. Now, if you look at the gray matter itself, the ventral horns, the ventral horns, which is the larger part of the wings of the butterfly, consists of cell bodies of spinal motor neurons. These motor neurons send their axons out through the ventral root, which consists of cables of motor axons on their way to supplying your skeletal muscle. And when these motor neurons are excited, they will produce contractions of your skeletal muscle. Conversely, in the dorsal horn, much smaller structure of this gray matter, you get mostly neurons that are sensory in nature. Sensory neurons. Okay. And for many of these sensory neurons, their cell bodies are not actually within the spinal cord itself. Their cell bodies are out here in the periphery in this cluster, this lump, known as the dorsal So you get a separation of sensory and motor axons, sort of like a separation of church and state. I won't say which is the church, which is the state. And again, here's ventral, here's dorsal. So there's a fair amount of processing occurring within this slab of tissue, the spinal cord. But for the most part, much of the higher level cognitive processing occurs in the cerebral cortex. Higher. So you literally, if you look at my first slide showing the entire human CNS, it literally is a hierarchy: spinal cord, brainstem, cortex. So to sum up, the human CNS is exquisitely complex. It receives a ton of sensory signals. It processes these signals in multiple cortical regions, which I just touched upon, the four major cortical lobes, to produce ultimately motor commands that enable our muscles to contract and therefore enable us to make movements. And without these movements, you cannot modify the environment. You cannot interact with your fellow human beings. So when something goes wrong, which is the central focus of clinical neuroscience, it's not always an easy task to localize the site of dysfunction, let alone to break down elucidate the mechanisms of the dysfunction, and then prepare a rational therapeutic strategy. But it all has to begin with a fairly competent knowledge of brain structure and functions. What functions can be ascribed to which brain structure. It's not enough to memorize the brain's anatomy. I mean, they may still do that in med school, hopefully not. It's essential to know functional neuroanatomy. So I'll see you in the future.
Those of you who haven't signed up